Okay, so now let's dig into the real, I don't know, for my part, one of the more interesting parts of this whole acoustics business, and that is spectral analysis, Fourier analysis. So just to motivate this, let's look at a handful of signals here. So here's three different signals, different waveforms, and you notice they're definitely different, but what's different about, well, you can subjectively describe the shapes, but really what we're interested in is in phonetics is identifying them. So here are the actual IPA symbols for the vowels that are represented here, but it's hard to read that off. And just to be clear, as a phonetician of more than a couple decades, I wouldn't be able to read those just off the waveform. I'd have to play them, or I'd have to convert them into some other representation. And this is where the real fun starts, um, where we get into Fourier analysis. Now, Fourier analysis is named after a mathematician from some time ago who conceptualized this, and he conceptualized it before we had the processing tools to really do the stuff with it that we can do now. Uh, but the idea is that every complex wave, remember we talked about complex periodic waves, quasi-periodic waves, noise, impulses, every wave that isn't just a sine wave can actually be mathematically decomposed or sort of broken down into a sum of sine waves. Uh, and what does that mean? That means we can represent what we know about sine waves. Any sine wave, we can represent it by an amplitude, a frequency, and a phase. With those three numbers, we can represent a sine wave. And so if we can break down a complex wave into a bunch of things that have those three properties, then we can really get a handle on it. And really, as we talked about before, the the phase isn't all that interesting to us. Mathematically, it's central to this kind of work, but once we've done the breakdown, we can kind of toss the phase away. Uh, right. So what happens then? Well, we have a sound, and now we can represent it as a set of, we have a bunch of different frequencies, different waves of different frequencies, and each frequency has a different amplitude. And that kind of representation is called a spectrum, where we have frequency along the bottom and amplitude vertically. Okay, so here we have a representation of those same three vowels. I could play them for you. Could have played them before, couldn't I? Here we have here's the one on the left, one in the middle, one on the right. So these are computer generated vowels, which is why they sound a bit artificial, but it gives a nice clean signal here. And in fact, as we'll learn over the next couple of weeks, this is very informative. We can see different peaks, different patterns of peaks. Here we have two peaks near the low end, and then a peak up here. The E, we have a peak down here, and then the next two peaks are up here. For U, we have the first two peaks are a little more separated than A, but not nearly as separated as for E. Uh, and the third peak is a little bit lower. So that distribution of the peaks is characteristic, and these representations are something that linguists can look at and okay, I bet that's E-like, or we'll get in the same general region. So that is very informative. Um, and the only thing is with a spectrum is that it doesn't give us time, right? Those spectra, uh, each one was computed over the whole length of that vowel recording. So if something was changing over that time, a spectrum wouldn't tell you something is changing, right? Um, a couple of other things just to note there. Um, one other thing, note the sort of regular, a bunch of regularly spaced vertical lines here. Those are called harmonics, and that's a common feature of periodic waves, complex periodic waves. We'll get into them in a later uh, module, uh, but they're quite interesting as well. But one thing that we would love to be able to do would be to get something like that information, but also represent how it's changing over time. And there is a way to do this. So first of all, rather than just take one spectrum over your entire recording, you window it. You say, okay, I want a spectrum of this little slice, usually a few milliseconds. And then you move over a bit and you take another slice. You move a few more milliseconds on and you take another slice. So you get a bunch of different slices, and then you have your time varying representation. And that's what we call a spectrogram. So here's a couple of spectrograms. Um, and here, time is represented horizontally, like it is for a waveform. Frequency is vertical instead of horizontal. And then you notice how there's darker and lighter areas. That's a third dimension that represents amplitude. So every vertical slice here is basically a spectrum. It's frequency mapped across different amplitudes, or different amplitudes mapped across the frequency range. And then we get a different slice each time we move forward in time. And we can see the sound changing over time. So this is really, really helpful. Um, One of the things that you see in there, let's get back to it. You see these two different representations. The first one on the left it kind of has a vertical striation look to it, and you see these very clean breaks in time. So the time, it changes abruptly from this sort of messy, this is noise, to something that's almost silent. You get a little pulse there, and then you have these sort of regular pulses for a voiced sound, another silence, another impulse, and so on. Uh, but you see every one of those vertical lines is kind of blurred out. Um, what's happened here is we're taking a really narrow window. And the thing about a narrow window is there's not as much information there for the Fourier analysis to pull out to get really precise frequency information. So the narrower the window, the more blurring you have in the frequency range. The spectrogram on the right, you have uh, actually some fairly fine detail. You see some of those regularly spaced comb-like structures that we saw in the spectra, but you notice that things don't happen quite as abruptly in the time domain. You get a fair amount of blurring on the horizontal dimension. And what's happening here is that we've got a longer window. You notice in the caption at the top, first window is 5 milliseconds, the second one on the window is 100 milliseconds. So 100 milliseconds of information, that's a lot of information, so we can get really fine frequency information. But as we move along, if you're moving along in, say, 5 millisecond increments, there's a lot of overlap between this 100 millisecond window and the next one and the next one. So there's going to be a lot of blurring in time because not a lot changes over those windows. And so that's the trade-off that we have with this windowing is a narrow window gives us good time resolution and poor frequency resolution. A wider window gives us better frequency resolution, worse time resolution. And one of the things that you see, uh, you can play around with it. That's 5 to 100 milliseconds. For this speech, I actually find 10 milliseconds is pretty good. We've got pretty good time resolution, and we're starting to see finer details in the frequency resolution as well. So it's, you can usually find, and 10 isn't always going to be the best. It depends on the voice and the context and whatnot, but a good balance between the two. Okay. So there's some more stuff in the textbook about windowing that's worth looking at, details about windowing. Spectrogram spectrograms are the most commonly used acoustic analysis visualization in phonetics, in my experience. Uh, Now I'm just going to close off with this representation. So this is that same E vowel represented, right? And we see on the left, this is a narrow band spectrum, beg your pardon. So this is with a very long window. This is the entire sound that you heard. And so you get the fine harmonic structure, these sharp vertical spikes, and the overall shape up, down, and down. With a shorter window, you still get the broad up, down, and so on, but you don't get the fine comb structure so much. And then linear predictive coding, which doesn't use Fourier analysis, but it does give us a spectrum-like representation. And we have it starts high, and then we have those two peaks later on. It's got a bit more swooping nature to it than either of the other two. And linear predictive coding has been used a lot in speech technology because it can be done really quickly. It doesn't take quite the same computational uh, uh, resources as the spectrum and the spectrogram take. And so you can read in the textbook about the LPC, the linear predictive coding system, and the Mel frequency capture coefficients, which are used for other purposes. Um, we're going to hit Mel's again later in this course when we talk about perceptual stuff. Uh, so there's a lot in there about how we can dig into a sound and get more information out of it. We will be using these tools and especially the spectrum and the spectrogram a lot over the coming weeks as we dig deeper into the acoustics of particular speech sounds and how all the articulatory stuff that we've learned about connects and translates into the acoustic realm that we've just covered.